Hey everyone, and welcome back to the channel. Have you ever taken a moment, a real moment, to just look at the world around you? Not just a quick glance, but a deep, curious look. If you have, you might have noticed something incredible. Nature, in all its wild and untamed glory, is secretly a master mathematician and a brilliant artist. It's a gallery of the most intricate and beautiful designs, all built on the language of numbers and shapes. From the tallest giraffe with its patchwork of polygons, to the delicate dragonfly with its fractal-like wings, and even the way a simple tree stretches its leaves towards the sun, everything is a symphony of geometry. It's easy to miss, but once you start seeing it, you can't unsee it. Nature isn't just random, it's an art form deeply connected to mathematics. Today, we're going on a journey to uncover these hidden secrets. We're going to explore how nature uses mathematical principles to create everything from the tiniest snowflake to the largest galaxy. So get ready to have your mind blown, because we're about to see the universe in a whole new light. Let's start with something we've all seen: a honeycomb. Have you ever wondered why bees, these tiny architects, build their homes with perfect hexagons? They could use squares, triangles, or even circles. So why hexagons? Well, the bees figured out something that stumped human mathematicians for centuries. The hexagon is the most efficient shape for tiling a surface. It uses the least amount of wax to hold the most amount of honey, and it leaves no wasted space. It's a perfect solution to a complex problem of optimization. It's not just efficient, it's incredibly strong. This hexagonal structure distributes weight evenly, making the honeycomb surprisingly durable. The bees didn't go to engineering school. They just tapped into a fundamental law of geometry. Now, let's move from the hive to the garden. Look closely at the head of a sunflower. You'll notice the seeds are arranged in a mesmerizing pattern of intersecting spirals. If you count these spirals, you'll find something amazing. There are usually 34 spirals going in one direction and 55 in the other, or maybe 55 and 89, or even 89 and 144. Do these numbers sound familiar? They are consecutive numbers in the Fibonacci sequence. This sequence, where each number is the sum of the two preceding ones, 1, 1, 2, 3, 5, 8, 13, and so on, appears everywhere in nature. This spiral pattern, known as the Fermat spiral, is the most efficient way to pack seeds into a circular space. It ensures that every seed gets the maximum exposure to sunlight and air with no crowding. The plant essentially solves a packing problem using Fibonacci numbers to achieve perfect harmony. You can see the same principle in the scales of a pine cone, the structure of a pineapple, and even the branching of a cauliflower. It's a universal growth algorithm, a piece of code written into the DNA of the plant world. And speaking of branching, let's talk about fractals. A fractal is a shape that repeats itself at different scales. Think of a tree. A large trunk splits into smaller branches, which then split into even smaller branches, and those split into twigs. Each small part of the tree looks like a miniature version of the whole. This self-similarity is the hallmark of a fractal. This pattern isn't just for show. For a tree, this branching structure is the most effective way to maximize its leaves' exposure to sunlight for photosynthesis. For our own bodies, our lungs use a fractal branching pattern. The trachea branches into bronchi, which branch into smaller bronchioles, allowing a massive surface area for oxygen exchange to be packed into the small space of our chests. Our circulatory system, with its network of arteries and veins, follows the same fractal logic. Nature uses this repeating pattern to efficiently fill space and transport resources. It's a design of infinite complexity, born from a simple, repeated rule. From the jagged coastline of a continent to the delicate structure of a snowflake, fractals are nature's signature of organized chaos. Even the symmetry we find so beautiful is rooted in mathematics. Think of a butterfly. If you draw a line down the middle of its body, the wings on the left are a perfect mirror image of the wings on the right. This is called bilateral symmetry. It's the same symmetry we see in our own bodies and in countless other animals. This body plan is advantageous for balance and movement. A starfish, on the other hand, has radial symmetry. You can rotate it around its center point, and it looks the same from multiple angles. This is perfect for an organism that needs to sense food or danger from any direction. These aren't just aesthetic choices. They are functional designs refined by millions of years of evolution. Symmetry is a solution. It's nature's way of creating balance, stability, and efficiency. Every symmetrical leaf and every mirrored wing is a testament to the power of geometric order. But what about the things that seem truly chaotic, like the waves of the ocean or the patterns in the sand? Even here, mathematics can help us find order. The science of fluid dynamics uses complex equations to model the behavior of liquids and gases. While we can't predict the exact shape of a single wave, we can understand the underlying patterns and forces that govern them. The ripples in the sand, the swirls in a river's current, the magnificent spirals of a hurricane, they all follow physical laws that can be described mathematically. And let's look up to the grandest scale of all. The planets in our solar system orbit the sun in elliptical paths, not perfect circles, as described by Kepler's laws of planetary motion. Galaxies, like our own Milky Way, often form breathtaking spiral arms, echoing the same Fibonacci spirals we saw in the sunflower. The universe itself, on a large scale, appears to have a structure, a cosmic web of galaxy clusters and voids. From the microscopic to the cosmic, the fingerprints of mathematics are everywhere. So what does this all mean? It means that the universe we live in is not just a random collection of stuff. It's a place of profound order, structure, and elegance. The laws of mathematics are not just human inventions we use to describe the world. They seem to be the very framework upon which the world is built. It's as if nature has a deep, innate understanding of geometry, optimization, and physics. When we admire a beautiful flower, we're not just seeing colors and petals. We're seeing a solution to a packing problem. When we watch a bird soar, we're witnessing a masterclass in aerodynamics. And when we look at our own reflection, we see a marvel of bilateral symmetry and fractal networks. This perspective can change the way we interact with the world. A walk in the forest becomes a geometry lesson. A day at the beach becomes a study in fluid dynamics. It fosters a deeper sense of wonder and connection to the natural world. We realize that we are part of this magnificent mathematical tapestry. Next time you're outside, I challenge you to look for these patterns. Count the petals on a flower. You'll likely find a Fibonacci number. Notice the branching of the trees, the symmetry of a leaf, the spiral of a snail's shell. You are surrounded by genius. You are walking through the greatest art gallery and the most advanced laboratory that has ever existed. Nature is the ultimate artist and engineer, and its language is mathematics. By learning to read this language, we gain a more profound appreciation for the beauty, complexity, and sheer intelligence of the world around us. It's a secret hidden in plain sight, waiting for us to discover. Thank you so much for joining me on this mathematical journey through nature. I hope it's opened your eyes to the hidden order all around us. If you enjoyed this video and want to explore more amazing secrets of our universe, please hit that like button and consider subscribing to the channel. It really helps us create more content like this. Don't forget to ring the notification bell so you won't miss our next adventure. Until next time, stay curious.